Chapter 15, Lesson 3. Last time we finished with a few example problems, and in this lesson we'll actually do two equilibrium problems together. Let's do this one next. Example 8. Reading the problem, it states a closed system initially containing this much H2, and this much I2. And by the way, here's the equation. H2 reacting with I2 producing 2HI. The system is allowed to reach equilibrium. An analysis of the equilibrium mixture shows that we have this much HI in the system at equilibrium. And then we want to calculate Kc. So this is going to be the first example where we calculate the equilibrium constant based on experimental measurements, essentially. So remember, the central idea of this chapter is the calculation of this equilibrium constant. In this case, it's going to be in terms of concentration. So here we're going to distinguish between two concentrations. These top concentrations here are the initial concentrations, the starting concentrations. So in an equilibrium problem, you're oftentimes are going to begin with initial amounts, the beginning amounts. You can think of these as at the beginning of a chemical reaction, and then the reaction is going to reach equilibrium. Remember that with many of these systems, the reaction doesn't really stop, it doesn't really finish. We simply reach a state of equilibrium. And then we're going to be given equilibrium concentrations, and we'll be asked to do some calculations. So always keep in mind these two steps. And this will be the starting concentrations, and this will be the equilibrium concentrations. And it's just in this problem, that's exactly what we'll have to do. Now, in order to help us solve these types of problems, anytime we have both starting and equilibrium concentrations, so initial and equilibrium concentrations, we're going to use what's called the Icebox. And this is a very common method developed some time ago that most instructors use. So what this means is that we're going to keep track of the initial concentrations, the change in concentration as we go to equilibrium, and then finally the equilibrium concentration. So this is our Icebox. So from this problem, we know that initially we begin with a bunch of H2 and a bunch of I2 and nothing of HI. And we're going to assume there's nothing of HI because the problem does not tell us. Technically what we're doing is we're just putting these reactants in the system. And remember, this is a double arrow. And then we analyzed the equilibrium mixture and found this amount of HI. And in order to calculate the equilibrium constant, recall that the equilibrium constant, in our case Kc, is products over reactants. Now the balanced equation shows that we have 2 HI. In fact, if you take a look at the previous slide, here is our balanced equation. So considering the fact that we have 2 in front of the HI, we'll have to, for our equilibrium constant, we'll have to put HI in brackets to the second power, and we'll divide by the concentration of both H2 and I2 multiplied by each other. This is how the equilibrium constant is defined. And these, the numbers that will come in here, will come from this equilibrium from these equilibrium concentrations. So we already have HI that we can put directly into the expression. We still have to find H2 and I2, and the way we're going to do that is we're going to think about the change that occurred as we went to equilibrium. So we know that we began with nothing of HI and ended up with 1.87 times 10 to the negative third. This can only mean that we've added this much. So we actually added 1.87 times 10 to the negative third, which makes complete sense. So stoichiometrically, if we added this much HI, we can ask, well, how much I2 did we lose? And how much H2 did we lose? Well, we know that stoichiometry shows that it's a 2-to-1 ratio, so we actually lost half as much as we gained, which means if we divide 1.87 by 2, or 1.87 times 10 to the negative third, divided by 2, we'll find exactly how much we lost. And that's, we can say 0.935. So we lost 0.935 times 10 to the negative third in both these cases. Again, that was simply given us by stoichiometry. So this change step is actually coming from stoichiometry. You can put it this way. And since we know the initial and the change now, we can calculate the equilibrium concentrations of both of these. In this case, 2 minus 0.9 should give us 1 point, going to put that on your calculator, 1.065, 10 to the negative third, and then in this case 0.065, 10 to the negative third. And since we've got our equilibrium concentrations, we can plug these values now into the equilibrium constant and solve. So go ahead and put all these in. We got 1.87 times 10 to the negative third. Don't forget to square this quantity, divided by H2, which in this case is 0.065, 10 to the negative third, and I2, 1.065, 10 to the negative third. And go ahead and take them to put that into the calculator, see what we get. And we should come up with a value. And see whether you came up with 50.5 if we have three significant figures. So 50.5. Remember, the equilibrium constant does not have units, or we could derive some units, but we don't care about the units for the equilibrium constant. 50.5. Hopefully you got the same amount. So this is a pretty famous problem. Now we're going to do another problem that's very similar. This is going to be the last problem. But before we do that, I want you to take a note of something, because this will come up with the next problem as well. What we did is we essentially considered this 2 during the stoichiometry, during the change phase, and then we considered this 2 also in the equilibrium constant calculation. So we considered it twice, and many students get confused asking, well, didn't we already consider it? Don't we have to just do it once? In fact, we have to do it twice, because this is from the stoichiometry and this is from the equilibrium constant. So we do have to do this just by the rules of stoichiometry and equilibrium constant. That doesn't change. Okay, so let's try this last one. This next one, the starting concentrations of this reaction are given to us. These are the initial concentrations, and the value now is given to us 50.5. This is what we just calculated. And we're asked to get the concentrations of H2, I2, and HI at equilibrium. So notice what we're doing is we're doing this problem backwards now, as we've done the previous one. And this is going to require a little bit of extra math, and hence the designation here as double diamond, in honor of a difficult slope. So let's go ahead and set up the icebox. Remember, these are initial concentrations. So on the next slide, we'll go ahead and set up the icebox, and we'll have to work with the icebox as we've done previously. So usually it's customary to rewrite the equation first to help keep track of it. And then we have our icebox. So create an icebox like this. And reading the problem, we're given the initial concentrations of H2 as 1.0 molar and I2 as 2.00 molar. We'll assume that we have nothing of HI, otherwise they would have told us about it. So we have nothing of HI. We were also given the Kc, which was 50.5. Now, what they want us to find out are these three concentrations. And in order to do that, we'll have to consider the change as we go to equilibrium. So in this case, what we've got is we don't have any numbers. So we'll have to use algebra. In fact, what we can say is that in order for us to get to equilibrium, we have to lose HI. So these two must be negative for our change. These must be negative, and this one will have to be positive. And that makes sense because we begin with nothing of HI. We have to gain HI and lose I2. This is the direction, you can say, in which equilibrium will take the system. Because we don't know exactly how much we'll lose or gain, but we know that they're related, what we can do is we can say for every one of these that we lose, we're going to gain 2 of these. And for every one of these that we lose, we're going to gain 2 of HI. And that strictly comes from the coefficients. Remember, there's a 1 in front of here. So for every one of H2 that we lose, we gain 2 HI. And then in the equilibrium box, what we can do is we can combine these two. So down here we can put 1.00 minus x. Here we can put 2.00 minus x. And here we can put 2x. Now, because we only have one variable, we can actually solve for x. And that's the beauty of it. In fact, we know that the equilibrium constant, Kc, should equal products over reactants, as we've done before. We did this in the previous problem. We should know this is HI squared divided by H2 and I2. So what we could do, and these are, remember, equilibrium concentrations because this is the equilibrium constant. So we can actually plug these values into Kc and solve for x because we know what Kc is. Kc is 50.5. So essentially, here's what we're doing. We're saying that 50.5 is equal to Hi is 2x, and here we'll put 2x, and then we'll have to square this whole quantity because in the equilibrium expression, your concentration of Hi is squared. And here it looks like we've done it twice, but remember this 2 came from stoichiometry, and this 2 comes from the K constant, as we've discussed just a minute ago. And then let's divide by 1.00 minus x multiplied by 2.00 minus x. So it seems like we should be able to solve the problem as long as we know how to solve for x, as long as we know a little bit of algebra. So what we'll have to do is let's go ahead and multiply this over to the left side, and we'll have ourselves 50. We can say we can do this a few ways. Maybe before we multiply it out, let's go ahead and distribute it. So let's multiply this out. That way we have the bottom distributed. That may be a little easier. So in fact, instead of doing that, why don't we just distribute this. So we have 50.5 equal to 2x squared is essentially the same as 2x times 2x. If you recall, that means you multiply the 2's and the x's as well. You should get yourself 4x squared on top. On the bottom we have, if you distribute, it's going to be a long denominator, but we'll do 1 times 2 first, which gives us 2.00. Then we'll do 1 times minus x, so we got minus x. We'll do 2 times minus x, minus 2x, and then we'll do minus x times minus x, which gives us x squared, positive x squared. Combining these together, we can say we have minus 3x. So we have 4x x squared on top, 2.00 minus 3x plus x squared. And now we can multiply this quantity out in the front. So let's do that in the next step. We have 50.5 multiplied by 2.00 minus 3x plus x squared equals 4x squared. Let's go ahead and multiply these out, just carry it out, and then we'll combine like terms. So 50.5 times 2 is 101, minus 3x times 50, we have 151.5x, plus 50x squared equals 4x. We can now subtract the 4x on both sides, and then we'll get a final problem that looks like this. We have, and let's go ahead and arrange these. If you are seeing this from the math perspective, you're seeing that we'll have to use the quadratic equation at this point. And recall, to use the quadratic equation, we'll have to align all the x's together equaling to 0. So we'll put everything on one side, and that will equal to 0. So I'm going to put the x squared first. This should be a squared. So we have 46x squared minus 151.5x plus 101 equals 0. And now we'll essentially have to use the quadratic equation in order to solve for this. So get ready for the quadratic equation, and we'll do a little bit extra math here. So rewriting what we just had, we had 46x squared minus 151.5x plus 101 equals 0. Now, if you recall, the quadratic equation requires us to use a formula, the quadratic formula, and that formula looked something like this. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. This should be familiar to you from a math class, and if it's not, call up your math teacher and demand to know why this is not ingrained in your brain. So if you recall, the a, the b, and the c are simply the numbers in front of the x squared for a. This is your a term. This is your b term, and our c is our constant. So it's really a matter of plugging them in and solving it. So negative b means we have 151.5 plus or minus the square root of negative 151.5 squared minus 4 times 46 times 101, all divided by 2 times 46. And I would recommend, as you're solving a problem like this, to go ahead and just, instead of plugging it all in at once, go ahead and do part by part and rewrite it. That way we're not missing any steps. This will actually help us tremendously to make sure that we do not lose any of these steps as we go along here. So let's try this. We got 151.5 squared. Let's rewrite this as 151.5 plus or minus. We got 22,952 for b squared $18,584 for the second term, and for the bottom we should have ourselves 92. Okay, let's keep going here. Let's go ahead and whatever is in the radical, let's go ahead and combine it. And we should get ourselves 151.5 plus or minus the square root of 4368 all over 92. And 4368 squared of 4368 can be further reduced to 66.09 plus or minus 66, we'll say 0.09 for significant figure's sake, 92. So if you recall, the quadratic gives you two values. That's why we have the plus or minus, and that means every quadratic equation has two x's, x values that we can solve for. Now one of them, in our case, will work, the other one will not, and we'll see how to figure this out as we go back to the initial concentrations. So go ahead and plug in. Let's do a problem where we use a positive and then a minus. So using the plus, we should get 2.365 for the x, and for the minus, this was using the plus, and for the minus, we should get 0.9. Oops, put this up here. It's not negative, it's positive. X is actually positive in both cases. 0.928 and 0.928 for significant figures. So these are our two x values. This equals x. Now one of these will work, the other one will not work. In fact, if you recall, our initial concentrations of I2 and H2, I2 was 2.00 molar and H2 was 1.00 molar. And these concentrations got reduced. And as they got reduced, we ended up with equilibrium concentrations. Now, we can't pick the first number. This first value that we've solved for actually cannot work. The reason this first value cannot work is because if we subtract 2.00 minus 2.365, we'll get a negative number. And you cannot have a negative concentration. That makes no sense. So this we can cross out, and then this is our real answer. This is the answer for x that we'll have to use. So if you go back to the original problem, we can now plug these values in to the icebox and solve. So for the equilibrium, if you remember the icebox that we had at the beginning, we were actually looking at these for these values here. And if you recall, this value was 1 minus x essentially. This was 2 minus x, and this was 2x. So, and this, recall, was HI, concentration of HI. This was the concentration of I2, and this was of H2. So we will now have to plug these values and solve for the equilibrium concentration. So for H2, we simply take 1 minus, or you can say 1.00 to be precise, minus 0.9284. 928 for three significant figures. And this should give us 0.072 molar for H2. This is our H2 concentration. For I2, we have a similar calculation. We have 2.00 minus 0.928. And if we plug this in, we have 1.07 molar. This should be a 7. And then finally, if we plug in HI, HI is 2x, which means we multiply 2 by 0.9284, and get ourselves 1.86 molar using significant figures. In this case, we would have to put a 0. And so these are our 3 concentrations. And this should conclude the lesson for us. A problem like this is quite involved, so we'll do a few more of these as we go along.